Hello and welcome to Algebra 2 with Mr. Clausen. Today I want to talk about graphing in 3 dimensions. And so specifically what I want to talk about today is how to graph a point within a 3D coordinate space, and then follow that up with talking about how to graph a plane in a 3D coordinate space. So without further ado, let's get started here. Now, whenever we're talking about graphing a point in a coordinate space, the main thing that you're going to notice that's a little bit different than what you've done in the past is that there are 3 points in describing a coordinate space. You have the x-axis, you have the y-axis, and you have the z-axis. And what you'll notice about a standard coordinate plane is that the x-axis is always pointed at this slant, y-axis is over here, and the z-axis is always straight up and down, right? Because if we look at a coordinate plane, like we tend to look at it as this 2-dimensional plane laying down. So when they add this 3rd dimension, they think of z typically as being up or down as far as defining that axis. All right, and if you're kind of like, well, why isn't this y and this x here while this new, so to speak, line is z? This is just how they chose to do it, and if you go into any engineering related field or you're ever looking at AutoCAD software, this is the orientation that they're going to put it in. So this is what you're going to want to get used to. There's nothing really wrong with it, and honestly, if you're ever going from 2-dimensional to 3-dimensional, I think this makes a lot of sense to do it this way, especially if you start thinking about like right thumb rule and certain physics applications when you're talking about force and that type of thing. And I'm not going to get into all that right now, but there is intentional reasoning for the distribution of these points. So the first point I'm going to graph here is x at -1, y at -5, and z at 0. Since I see that z is equal to 0, I can tell that my point is going to be on the xy plane here. So it's going to be laying down like we typically would see it. And so what I'm going to do here is I see x at -1 goes this way. So I'm going to go and draw that distance. I see that y is at -5, so I go -5 in this distance. So what I'm going to do is I'm going to create a little parallelogram here, and I'm going to go and make a line parallel to the x-axis here that is the same length as this segment here, and then parallel to the y-axis, the same length as this point here. And I don't expect perfection, but I expect it to look sort of like a parallelogram. And then what I'm going to do is I'm going to highlight this point here. All right, and this point is going to represent -1, -5, 0. And the main idea here is that we're just drawing the parallelogram to show how the point relates to the space here. I can see that it is within the xy axis. It has nothing to do with the z-axis. It's flat within this plane, and that it's laying out in this point here. The same thing could be said if we had x equal to 7, y equal to 0, and z equal to -2. Here I can see it's in the xz plane, so I expect it to kind of be sticking up here. And so if I go 7 from the origin in the x direction, right, I'm going to have this segment here. I'm going to go in the z direction by -2. And then what I'll do is I'll make a line parallel to the z-axis about 2 units in length, and parallel to the x-axis 7 units in length. Again, just trying to make that parallelogram. And here I have the point 7, 0, -2 that describes the distance from the origin in this space. Now, if we want to make it a little bit more complicated and use all 3 dimensions, which we want to be able to do, we're going to start making these cubes. All right? And so, again, we're just trying to describe how the point relays in space. And by constructing these objects like parallelograms and cubes and those type of things, it's the best way we have to do it by hand. Now, when you use AutoCAD software and all that type of stuff, it does a really nice job laying all that out, but just for describing the skill and getting you guys just a brief introduction to this, we're just going to draw the cube. So again, I'm going to do the same thing. I'm going to go -4 in the x direction, -7 in the y direction, and -1 in the z direction. All right, so you can see my relative vectors in each direction. And now I'm going to start just making a cube here. All right, so I'm going to go from this point and make a line congruent and parallel to this, but from this point, right? So I'm going to copy this line right here, and I'm going to move it over here, and then I'm going to make a copy of the line on the y-axis and put it up here. I have 4 vertices now, so now what I'm going to do is I'm going to take this line that's on the z-axis here and duplicate it here, here, and here. And I'm just trying to make the points approximate in length right now, and then copy the y-axis lines and the x-axis lines. And now I've made this prism. All right, and I can see based on this prism that if I go from here to here to here, that this is my point being represented 3-dimensionally. And I'm going to expect you to bold the point a little bit so I can clearly see what it is. But now I can see how that point lays out in space. If you just draw a random point, I mean, you could draw it almost anywhere on the paper and try to make some type of argument that that's your point. But drawing the prism allows the viewer to very clearly see how you're trying to lay it in there in terms of the 3-dimensional space. So I would draw a prism like this to go and describe -4, -7, -1. And what I'm going to be looking for is, all right, how do you translate it across? How squared up is your cube? And those type of things in terms of describing that space. Let's do one more just for good practice. X, Y, Z. If you want to pause the video and practice real quick and then confirm your solution, you may do so, or you can just follow along as well. Now, you have X at 5, Y at 6, and Z at 7. Okay, so we're describing a little bit bigger cube example here, but the same thing applies. So I'm going to go draw it. Again, it doesn't have to be perfect, but it should look like a parallelogram. All right, so we have the parallelogram on the bottom. All right, and we have to draw all 6 sides of this parallelogram. There's another side of the parallelogram. There's another side of the prism. Alright, now we're connecting all the other sides. Alright, so now I've drawn this 3-dimensional prism, and it's this point right here that's furthest away from the origin of the cube that I'm most interested in, and this is the point that's representing 5, 6, 7 as the ordered triple. Alright, so this is how you graph some points in a coordinate space. Now what I want to talk about is how to graph a plane in a coordinate space. And the easiest way to graph a plane in a coordinate space is to go and identify the x, y, and z intercept and then draw it out. And that's what I'm going to ask you to do as a part of this lesson. So for example, if we look at a situation where x plus y plus z is equal to 2, what I want you to do is find the x, y, and z intercept. And just like you would do in the past, you know, if it was an xy intercept, what you do is set y equals to 0 and then figure out what x is, and then set x equals to 0 and figure out what y is. Well, with an ordered triple, what you do is temporarily assume that x is equal to 0, y is equal to 0, and if x is equal to 0 and y is equal to 0, and you just kind of cover those up, well, then z would have to equal 2 in order for this to be a true solution. Same thing with if you wanted to figure out what the y-intercept was. Assume that x and z are 0. Well, then y would have to equal 2 in order that to be true. And then if you want to figure out what the x-intercept is, temporarily assume that y is equal to 0 and z is equal to 0, and set x equal to 2. And those are going to be our 3 solutions, one being the z-intercept, one being the y-intercept, and one being the x-intercept. And all you need to do to sketch a plane is to go and dot out these points. Dot the y-intercept, the x-intercept, and the z-intercept. And you should have a point on each axis. But then all I'm going to ask you to do is draw a line connecting each pair of dots present. So there's 3 lines, so there should be 3 points. And then shade the triangle that is formed. And what you're doing is you're just identifying a small sliver of the plane that you can represent very easily using the y, z, and x intercepts. And this problem would be complete. This is what I would be looking for an answer in terms of graphing a plane in a coordinate space. So let's beef up the example a little bit. So let's temporarily assume that x and y are equal to 0. So that tells us that, all right, well, let's find the z-intercept. Negative 4z is equal to 8. If x is equal to 0 and y is equal to 0, then z would have to equal negative 2. That tells me that the z-intercept is 0, 0, negative 2. That point is right here. All right, if I want to find the y-intercept, I'm going to say negative y is equal to 8. All right, that's because I'm plugging in 0 for z and 0 for x. So the y-intercept, because I'm plugging in 0 for x and 0 for z, is going to equal negative 8. That's going to be my order triple there. So the y-intercept is over yonder. All right, and if I want to find the x-intercept, well, just say x is equal to 8 because we're going to cover all this up, the y and the z part. So the x-intercept is just simply 8. And then 0 for y and 0 for z. All right, and that's going to be over here. All right, and so now we have our 3 vertices, all right, 1 on each axis. And I'm just going to draw a line connecting those 2 points. Draw a line connecting these 2 points. And draw a line connecting those 2 points. And then I'm just going to shade in the triangle. And what you're going to see is this kind of downward sloping plane that is going, and it's representing the plane in the coordinate space. So with that said, that's all I have for you with these examples. Hopefully you've gotten an idea of how to graph a point and a plane within a coordinate space. And with that said, let's do some math.